here we go with our next physics presentation here. And before we get started, let's just check in a little bit and let me ask how you're doing with the physics. We're well into the first marking period now, so you have an idea of what the class is all about, and hopefully it's getting you scratching your head a little bit. I'd like you to get to the point where we're challenging you in the high school so that you can develop your thinking. And physics is definitely one that can get people thinking a little bit. So maybe it is challenging to you right now, but this could be an opportunity for you to turn something that's challenging into something that you can master. And that's always good, always good. That'll stick with you for a long time. So we're going to always try to give you information, but not have you just give the information back to us, to see if we could take it a little bit further. And you'll see in some of the questions that we ask, it's not exactly like we talked about in the presentation. You try to take it a little bit further. And it's always a good idea with information that you're given to think about that. Where could it go from there? Where could you possibly take that? So we're going to take our one-dimensional motion a little bit further, and we're going to talk about free fall motion. So free fall motion is going to be something that is flying through the air. Here's a ride. You may have seen the free fall ride. That's a fun one, and people seem to like that when the gravity drops out from underneath them. So we'd like you to ask questions, and speaking of that gravity, what could benefit us? Besides an amusement park ride, what could benefit us by understanding how gravity is going to affect motion? That's a good thing to think about. So without giving you the answer, there's something for you to try to take the information and go a little bit further with it. Maybe we can talk about it in class. Okay. So we're going to be talking in our discussions about things that are falling through the air, and we have the idea now that objects pick up speed as they fall to the ground. And we have a word for that, picking up speed, and that's acceleration. So we have the idea that as things are falling, they're going to accelerate, they're going to pick up speed. And in test after test after test, they've found that gravity causes things to accelerate at 9.8 meters per second squared, and it doesn't matter what the object is, it's going to accelerate at 9.8 meters per second squared. Now how about that as a jumping off point to think about things that you know about in real life? Is that what you see? Everything falling at the same rate? A leaf off a tree and a rock that's thrown? So think about that. You know, does that really make sense, what I just said there? And what could that mean? Where could we take that kind of thought process? But at any rate, while you're thinking about that and other things, I'm going to tell you that this 9.8 meters per second squared is so important that it has a special letter to it. It's the lower letter G. It's the acceleration due to gravity in a local area. And for us, our local area is Earth. This would be different places in the universe. And for right now, we're going to stick with all of our problems as if we're at sea level on Earth, where it's 9.8 meters per second squared, roughly 9.8 meters per second squared. But we'll use that number in our calculations, and it's pretty close to what it actually is. Okay, so that's the idea of the small letter G. So far, our problems will be at sea level on Earth, and later on in the class, we'll talk about how gravity would be affected on other places. And actually, we'll talk about that a little bit in this presentation. Okay, so there's the G, the 9.8 meters per second squared. Okay, so speaking of other places, how about the moon? Is the acceleration due to gravity on the moon different? Right now, we'll just talk about it conceptually. Later on in the course, we'll start making calculations. But yeah, do you think it's different on the moon? Do you have any experience with that? Why do you think that it might be different on the moon? Well, turns out that it is a lot less on the moon than it is on the Earth. And if you were going to jump on the moon, you could jump a lot higher than you could on the Earth. And when the astronauts went there, if you believe that, some people think it's a conspiracy theory and we never went to the moon. But when the astronauts went there, they did see that effect. They could hit a golf ball farther. I think they brought a golf ball with them. Okay, it's about 1/6 of what we have on the Earth, so it's a lot less. All right, what other things could we ask about the moon? Like I say, it's always a jumping off point. If you know one thing, what other things could you be thinking about? What other questions could you ask about the moon? It's a good one to come back to class with. What other kind of questions could we ask about the moon? I'll leave that one for you to think about for now. Always try to take what you're given and see if you can take it someplace further. If this is true, then what else is true? And that's a great thought process to go through in physics and in all your subjects. So you take your thought process a little bit further. Well, here's an apple falling off a tree, and that's got a famous place in physics history because speaking of taking things further, Isaac Newton, they say, saw an apple fallen from a tree and came up with the idea of gravity and realized that it was the same force, gravity, that made the apple fall as the moon go around the Earth. So there's a pretty good kinematic question to be asking about the moon, kinematics being motion. So there's the apple, and I'll do a problem with an apple falling from a tree. So I'll do it after you try it on your own. That would probably be the best way. Could you figure out where to set this one up? Would you pause and see how far you can get? Okay, are you back? All right, well, let's see how you did on this one. First of all, there's a key concept in a problem like this. If something falls out of a tree, then it has an initial speed of 0. So that's a good starting point with the apple. Also, because of gravity, the g value, 9.8 meters per second squared in our calculations, well, that's an acceleration. So here I'm plugging in that g value of 9.8 meters per second squared, and we're told in the problem that it takes 0.4 seconds to fall, right? So if it's 0.4 seconds to fall, then there is the time, the 0.4 seconds, and we're looking for the distance. How far did it fall? Well, here's our newest, our third kinematic equation, and this one will work out great for this situation. Always what you're doing is taking a look at the variables. Now that we're adding equations, there's more tools in the tool chest, if you will. So what we're doing is we're identifying the variables always, and that leads us to the calculation that we might use, or the formula that we might use. This is a good one. It has distance in it. It also has initial velocity, time, and acceleration. So all the things that we're looking for. Let's see how it plays out algebraically, because the algebra is pretty tricky too, along with the physics. All right, so when we plug this in with the initial velocity of 0, that's nice. This is going to cancel out. Here's one. 1/2 multiplied by 9.8 is 0.4 squared. So there's a first substitution to be looking at, and now I'll reduce it a little bit more, showing you the 0 here, so that cancels out to 0, 0 multiplied by anything, and 1/2 multiplied by 9.8, there's your 4.9 multiplied by the 0.4 squared. So this 1/2 of 9.8 is going to come up a lot. You're going to get used to that idea of 1/2 of 9.8 equaling to 4.9. Okay, so when we play this out, it turns out it falls 0.78 meters, and there we go with our first free fall problem. Okay, well, did that make sense? How did you do? Does it make sense now that I've gone over it? If not, bring your questions to class. We'll see what we can do with that. All right, let's try another one. All right, so here's a guy falling bricks. This is a bad move. If you're putting, if there's falling bricks and you think you're going to protect it with a newspaper, it's not going to work. And I don't think you have to need to know too much physics to know that this is a really bad plan. But you know, whatever. Hopefully the guy's okay. I don't want to see bricks falling on his head. That's just not going to do it. All right, so let's see. A brick is dropped off a building. Hopefully nobody's in harm's way. So dropped from a height of 65 meters. How long did it take to hit the ground? All right, well, let's take a look at this one and see what we can make of it. All right, well, here's that gentleman. Fallen, so it's a 0 meters per second. The acceleration is due to gravity, 9.8 meters per second squared, and it falls 65 meters. We're looking for the time. Again, this is a good equation because we have the distance, we have the initial velocity, and we have the acceleration. We only have one unknown. And again, since the initial velocity is 0, that's awful nice because this is going to drop off. All right, so this time I've put in the distance and the 1/2 9.8. Do you have it already? You know what 1/2 9.8 is going to be? Well, sure enough, 4.9 multiplied by t squared, reducing as we go. All right, I have two things to take care of here. The square and also the 4.9. So I'm going to get rid of the 4.9 first. I look at the square as being closer to the t, and I'll get the thing farther away. This is t squared. It's right attached to it. So I'm going to get rid of that 4.9 by division. And if I divide both sides by 4.9, I'm going to get 13.3 is equal to t squared. I do not want 13.3 as my answer because this is still t squared. I want to know what the time is. But I can undo the square by taking the square root of both sides. So if I take the square root of 13.3, that's equal to the square root of t squared, and that's t. And I can do a little bit better than the square root of 13.3 by using the calculator. And it's going to come out to 3.6 seconds. So that's my time. All right, so how did you do on that one? Did that make sense? Hopefully you challenged yourself by pausing. I forgot to remind you, but hopefully by now you know. All right, well, these problems will give you a good guide for when you have free fall practice problems to be working on. Okay, so let's see here. Here's another one for you. Here's a penny and a tall building. So the penny is dropped off of a tall building, takes 5 seconds to hit the ground. What was its speed? What is its speed when it hits the ground? Okay. Yeah, they do the Mythbusters on this. People talk about how much damage a penny could do if it's dropped from a tall building. It's good conjecture. But let's see here. All right, well, let's see what we got going on. First of all, what do we know already? Oh, there goes the penny dropping. Check that out. Oh, man, look at that penny go. I'll tell you what, if this is to scale, that's a really big penny compared to the size of that building. Either that's a really small building, or that's a really giant penny, or the thing is just not to scale. I'm not sure. But there you go, penny dropping. How about that? All right, so what do we know? The initial speed is 0. The acceleration due to gravity is the 9.8 meters per second squared, and the time is 5 seconds. So we want to find out the final speed. It's speed when hitting the ground. See, here again, now that we're getting more equations, it's important to identify the information so that you can pick the equation that you want to use. Later on, we're going to have so many different equations. Right now, it's only 3, and it's already getting complicated, this physics. But if you practice, you can do all right. Okay, enough philosophy here. Here's the equation that'll work. Plug in what we know, and that means the final speed is 49 meters per second. And there you go. That's it for these type of problems, I think, for the examples. We'll see how you do when you practice them. Okay, so let's see. Finish this statement here. What goes up must come down. That's exactly right. All right, and this is because of gravity. So things are going to slow down on the way up, a negative acceleration, remember, from slowing down. And they're going to pick up speed when they come back down again. There's a symmetry to it. Slow down on the way up, pick up speed on the way down. So, of course, the acceleration would be negative 9.8 meters per second squared on the way up, because that's how we have a deceleration or a slowing down on our accelerations. All right, so we have a phrase for the total amount of time in the air, and that's the hang time. So just a little vocabulary there. The up time plus the down time is the hang time. And how do you think they're related, the uptime and the downtime? Well, it turns out that they're exactly the same. Well, they're exactly the same in as much as objects fall at the same rate. But yeah, the same time on the way up and the same time on the way back down. All right, so here we come to that question I asked earlier. Why is it, do you think, that objects don't accelerate at the same rate when you drop them? Here is a calculator being dropped. That goes pretty quick. Here is a napkin being dropped. All right, well, what is it? Is it that heavier objects fall faster? You know, what are the explanations for this? What can you think of? Is that what it is? Heavier objects fall faster? All right, well, that's a good theory. Now, again, I already told you that we have the idea that everything falls at the same rate. But we just saw an observation pretty easy that shows that that's not true. But how about the idea of heavier objects fall faster? Here's 2 napkins, right? So they're the same, they're not heavier. And now are they going to fall at the same rate? Here's the one crumpled up, there, and here's that one not crumpled up. So do they fall at the same rate? So I don't know. Heavier objects fall faster can't be the explanation, but you probably already figured it out. All right, so air resistance is the answer, right? So the air resists what's going on, and that's why some objects are going to accelerate at different rates than the 9.8 meters per second squared. That's the air resistance factor. Yeah, so if you're falling through the air and you hold out your arms, you're going to fall at a different rate than if you ball yourself up, right? You're going to fall a lot faster, just like the napkin that I showed you. Hey, how many people are going to do that? Are going to do the skydiving? I always thought I was going to do that, and I never got around to it. And now I don't think I will. So my advice is do it before your knees tell you you don't want to do it. I don't know, that landing could be a little rough. This person looks happy though. I don't know. Maybe I will try it. But there's always people every year who say they'll try it, and sometimes people come in with a video of themselves doing some skydiving. So if that's you, bring it in. We'd love to see it. All right. Well, when you're falling through the air, because of this air resistance, actually things will accelerate at different rates, but then they hit terminal velocity. And the idea of terminal velocity is you've gotten to the point where you don't accelerate anymore. You fall at a constant speed, and they call that terminal velocity, and that's due to air resistance. So that's the answer. Without air resistance, if we took the air resistance out, and they do that with giant vacuum cleaners, vacuum chambers, I should say, not vacuum cleaners, vacuum chambers, where they literally take all of the air out of a structure, and they can see that a feather will fall at the same rate as a brick. And we'll see. Well, you can check out some of those videos if you want, and maybe we'll watch some in class. They're pretty good. Go check them out on the YouTube, or whatever we're watching these days. Okay, so unless otherwise specified, no air resistance. It makes things a little bit more complicated, and we'll rule it out for the most part. All right, speaking of checking in with you, because physics is not all that easy, if you are struggling, remember that first step. That first step to every problem is identifying the information. Right now, we're still with just distance, time, speed or velocity, and accelerations. So those symbols that's it for now. It's going to get more complicated later, but you have time to catch up if you're still not getting it. And the units that go along with the symbols clue you in. And if you're missing points for units on some of the questions, then this is a great thing for you to get right now. And also when you're identifying variables, sometimes people have troubles. They think that a velocity is an acceleration or an acceleration is a velocity. The units will help you. So these are good ones to get down. The meters go with the distance, the seconds go with the time, meters per second is the speed, and meters per second squared is the acceleration. So I hope that's helpful, and I hope that this video was as well. But if you have any questions, bring them to class. We have some more things to talk about now, and I look forward to seeing you there.